All right, so this segues very nicely into this talk. So this is essentially a kind of a more of a network sciencey flavor talk. It's going to be looking at the interplay between network topology and the dynamics that are happening on the network. So we're going to be looking at resilient distributed algorithms to achieve distributed coordination of networks. And it's going to be getting at exactly the types of questions and the talks that Seth just gave and Tina gave in the morning. And looking at the interplay between the network topology and the dynamics. So the settings as follows. So you've got a network with n nodes, and you've got the standard interpretation of the edges. So an edge from I to j means that node I can send information to node j. And each node has access to potentially private information, right? So this information could be sensor measurements or some static value, it could be an opinion if it's a social network. There could be local operating conditions or data sets, local functions, and so forth. And the objective is that the nodes must coordinate or cooperate in order to achieve globally optimal objectives. Okay, so there are different instances of this problem. So, for example, the distributed consensus problem that we've already seen today is each node has some local static measurement, and the nodes have to reach agreement on some function of those measurements. You can look at the distributed optimization problem, where instead each node has a local function, right? So if you're thinking about the power generator context, each node may have a cost of generating a certain amount of power, and the nodes must cooperatively figure out what is the global vector that minimizes the sum of all these costs. Similarly, you can look at distributed state estimation, where the nodes are together measuring the state of some underlying dynamical system, which is evolving over time, and they must cooperate in order to asymptotically estimate the state of the system. So there's different algorithms, distributed algorithms that have been proposed to solve various instances of these problems. And the challenge here, going back to the themes that we've seen already, is what happens if certain nodes fail or are compromised by an attacker, and these adversaries can be worsted. All right, so as we've seen already, a single attacker can cause major problems in existing algorithms. And so this idea of how do you come up with resilient distributed algorithms is very classical. It goes back 30, 40 years in the computer science literature. And the classical result has to do with the connectivity of the network. The connectivity of the network is how many different paths are there in the network between any two nodes. When we say different paths, we mean vertex or node disjoint paths. How many independent ways can I send information through the network? So the classical result is if you have up to f bad guys, and these could be arbitrarily behaving bad guys, the nodes can reliably exchange information if and only if the network is 2f plus 1 connected, meaning I can send information 2f plus 1 different ways through the network. Okay? So this is fundamental, right? So if your connectivity is less than this, you go home, because there's nothing you can do. If your connectivity is this or greater, there are in fact algorithms that allow you to do this and achieve resilience. So the classical algorithms would be sort of routing type algorithms where you explicitly send information to the network. We've done work in the past where we've shown diffusion type algorithms, like the stuff that we in control typically look at also are very powerful and allow you to achieve this and so forth. But the typical assumptions that are made here is that the nodes know the entire network topology. The nodes know a lot of information. They know the nominal dynamics of the other nodes. They can store data, so essentially they run whatever algorithm you're doing, but they gather the data they see during the course of this algorithm, and then they can do a bunch of computation on it and compare it to what they expect to be seeing, given that the network looks like this and the other nodes should be doing this. Right? And so based on that, you do sort of detection and isolation and so forth. So the theme here is that this is great, this is sort of getting at the best thing you could do in terms of network topology, but if we want to relax these assumptions and get at more scalable algorithms, so can we come up with mechanisms that don't require the nodes to know the network topology, they operate in a very lightweight way, they may not even know the number of other nodes in the network and so forth, can we still come up with a way to overcome adversarial behavior? Okay? And so, of course, there's going to be a trade-off between knowledge and achievable objectives, right? So essentially, if you're giving up so much, you're giving up on knowledge of the network topology, you're going to expect that you're going to have to pay a cost. And the cost is going to be in terms of stronger conditions of the network, which we'll identify, which Dina talked about earlier, and which the conditions that Seth talked about are a generalization of for more than scalar dynamics, and the achievable objectives will change as well. So let me just kind of refresh the memory about what these local filtering dynamics are. So suppose that each node in the context of consensus starts with some initial value xi0. So each node has a static value. And let's suppose that we consider the following mechanism. At each time step t, each node gathers all its neighbors' values, removes the highest f, lowest f, and averages the rest. Right, so that's the dynamics that we saw a couple times today. Okay, so I should say that these kinds of dynamics have been looked at in the computer science literature as well for special cases of networks. In 2012 and 13, which is put off here, Xenophon and our students managed to solve it for the most general case here, and in Illinois has also been working on this in parallel. Okay, so this looks very simple, right? It seems kind of obvious. Just throw away highest and lowest and average the rest. What's there to do? So, under what conditions will this guarantee convergence? That's the first question. Second question, the bad guys are not going to be sitting there and doing this. They're going to be doing arbitrary things. What can you say? So to gain insight into network properties now, because this is where we're going in terms of trying to understand the interplay between topology and dynamics, let's suppose that we look at a network that looks like this. So there's n over 2 nodes here, n over 2 nodes here. Everybody's connected to everybody else, everybody's connected to everybody else, and everybody here has exactly one friend in the other set. And suppose everybody here has an initial value of 0, that's their sensor measurement. Everybody here has an initial value of 1, that's their measurement. And these guys want to reach consensus, but they're suspicious of there might be one bad guy in the neighborhood. So they're going to apply the dynamics I talked about, where they throw away the highest and lowest and average the rest. So what happens here? This guy wakes up and looks at the neighbors. Everybody here says 0, one friend says 1. When they throw away highest and lowest, they throw away the 1, average the rest, they stay at 0. Right, so everybody here stays at 0, everybody here stays at 1, consensus is never reached. Okay, there aren't any bad guys in this network, everybody's just following the dynamics, but still consensus isn't reached. This is a beautiful network from the perspective of any classical metric of robustness. Everybody's connected to half of the other people in the network. The connectivity of this network is n over 2. Okay, so if everybody knew the network topology, they could tolerate n over 4 bad guys and still reach consensus. But here, without any bad guys, just because you're doing these purely local dynamics, this beautiful network still doesn't facilitate consensus. Okay, so something more has to be said, and so this leads to this idea of robust networks, which Xenophon talked about a version of this morning. So the problem here was that we could take this network, we could split it into 2 sets, where neither set had a node that had enough neighbors outside its own set, right? Every node inside each of those sets was throwing away the only useful information it was getting from outside its set. So we need a new topological property to characterize conditions under which this does not happen. All right, so to do that, let's introduce the following notation. So I'll go a little bit more in depth here than what you found this morning, because this property is going to tell us something very interesting and cool about large-scale complex networks, which I'll get to at the end, so it's important that we understand this property. So if I give you a graph, and I give you a set of nodes S, we're going to say that that set S is R reachable if it has a node inside the set that has R neighbors outside that set. Okay? So just to illustrate, this green set here is 3 reachable because it has a node, B5 in this case, that has 3 neighbors outside the set. Similarly, this orange set here is 4 reachable because it's got a node, B7 in this case, that has 4 neighbors outside that set. Okay. So this R reachability is a set property telling you, is there a node that has enough friends outside? Okay, we're going to want a graph property. If I give you a graph for a network, I want to ask about will consensus succeed. So we're saying a graph is R robust if for every pair of disjoint subsets, at least one of the sets is R reachable. So we want to avoid the situation that we saw earlier where we could find 2 different subsets where neither set had a node that had enough neighbors outside. So this R reachability is going to characterize, the fact that no matter how you choose 2 different sets, one of the sets is going to get pulled towards the other. So in this graph, for example, no matter how you choose 2 different subsets, at least one of the sets is going to have a node that has 3 neighbors outside. So this graph is R robust, 3 robust. Is that clear? Is the definition clear? Okay. Any questions about it? All right. So the main result then is the following. Remember when we said if the nodes know anything about network topology, connectivity is the key, and 2f plus 1 connected is if and only if. Now when you're doing this local filtering dynamics, robustness becomes the key. So if the network is 2f plus 1 robust, as opposed to just 2f plus 1 connected, the normal nodes will reach consensus and the convex hold their initial values, despite the actions of any f local set of vector space. And f local means you can have up to f bad guys in the neighborhood of every good neighborhood. So you can have a huge number of bad guys in this network, not just f for the entire network, but f in every neighborhood. And no matter what they do, if the network satisfies this property, all the good guys will still reach consensus in the convex hold. So there's a safety pinch.
So this is the D equals 1 condition.
D equals 1. This is the case where the local values are scalars. Not
So
vectors.
if you have trivial copies of,
Yeah.
it should work.
It should work, but you won't reach consensus in the convex hull of the points. You'll reach consensus in the convex hull of the element
The Cartesian
lines.
product of the constant
Yes,
convex.
exactly. That's right. So if you care about consensus in the convex hull of the points, then you have to do more complicated things like Turberg points. Yeah. Okay. So takeaway point is that if the graph satisfies the required robustness property, these dynamics are actually really good. Okay, because you can get a lot. Okay, so here's just an illustration. So this is kind of the main intuition here. If the network is robust enough, basically the good guys, their values are getting pulled closer and closer together. The bad guys I've highlighted in blue here, if they go outside this range, they're going to get thrown away. So they can still try and influence the consensus value, but essentially they're getting squeezed, right? So if they want to have their values be used, they have to stay in the moderate range, and essentially that distance gets smaller and smaller if the network is robust. Okay. So just before I talk about what this robustness property means and its implications in large-scale random graphs, this idea of local filtering is actually pretty nice because it gives you a starting point to apply resilience or gain resilience in a bunch of different algorithms or different tasks. So remember I talked about distributed optimization and distributed state estimation. So let's talk about the distributed optimization setting where every node in the network has some local function f, and the nodes want to cooperatively calculate the minimizer of the sum of their, or sum or average of their functions. So if you look at a consensus-based distributed optimization algorithm, where each node maintains an estimate of the optimal state, or the optimizer of this, it exchanges its estimates with its neighbors, takes a convex combination of those, and then takes a gradient step. So this is what's new in terms of distributed optimization in order to account for the minimizer of its average. Okay. So this is, as long as the step sizes here are chosen properly, it turns out that if you follow these dynamics, everybody will in fact converge to the global minimizer. So again, if you want to make this resilient, instead of averaging everybody, throw away highest and lowest and average the rest. Okay, so same thing. So using this local filtering as a starting point to establish resilience in this class of dynamics, you can show very similar things. If the network is 2f plus 1 robust, and the step sizes satisfy certain properties, which are the same properties as a standard distributed optimization, then regardless of what any f local set of bad guys do, the regular nodes will asymptotically converge to the convex hull of the local minimizers of the regular nodes. Okay, so you still get some safety guarantee, and you get some sort of optimality where you're guaranteed to get within the convex hull the local minimizers of the local functions. Similarly, just to illustrate, you can apply these in a variety of different situations. Distributed state estimation, you've got some underlying system, you've got a bunch of nodes that are each measuring parts of this system, and the nodes want to cooperatively estimate the full state of the system. So you can do something very similar. So just to illustrate here for simplicity, let's suppose that the state is a scalar. Okay, then there are certain nodes that can directly measure the state. They don't have to exchange information with anybody else. There's some other nodes that can't measure the state, and if they use consensus dynamics, where they maintain an estimate of the state and they rely on their neighbors to give them estimates of the state, and they use consensus dynamics, and if you use local filtering, then essentially if there's another version of robustness that the network satisfies, because now you have certain nodes that are acting as leaders, they have access to the state, then by applying local filtering, all the regular nodes can still estimate the state regardless of what the bad guys do. Okay, so the theme is essentially wherever you have consensus-based coordination and you need resilience, local filtering seems like a great first thing to try. Okay, all of these things said, if the network is blah blah, then this works. Okay, so, and then we saw a network before that seemed great, but it didn't facilitate consensus at all. So the question here is, this is all predicated on this network having this property. How strong is this property, right? It's great that if the network has a property, great things happen, but maybe the property doesn't hold. So it's so rare that it's hard to get this property. So the question is, okay, if I want to run this in large-scale networks, the whole point is that I want scalable algorithms for huge networks, for complex networks. If I run this in large-scale networks, what would happen? Yes?
Now, before moving, I would like to ask you, why do you use R robustness instead of R robustness if the second one requires less connectivity?
The second one, so R robustness is a stronger, 2F plus 1 robustness is a stronger version of RS robustness.
Yeah.
And R robustness is only a sufficient condition, but it guarantees you resilience to F local sets of adversaries. Whereas RS robustness, F plus 1 robustness, is a necessary and sufficient condition for F total adversaries. So as long if your network has F total bad guys, then F plus 1 robustness is necessary and sufficient under the malicious model. If your network has F local bad guys, which could be much bigger, 2F plus 1 robustness is sufficient. Okay. But it turns out, as you'll see, something really cool, that this stronger condition actually holds in large networks. So you actually get a lot for free. Okay, so we've identified this property of networks, and it's kind of interesting now to try and figure out what does this set of R robust graphs look like, right? So this is a set of all graphs, again, not this scale, right? So you've got the graphs of minimum degree R, you've got graphs that are R connected, you've got graphs that are R robust. R robustness is a stronger property than R connected. Okay? So how do these sets compare? So let's think about different models for large-scale networks. So one of the most common models is the Shreyas random graph. Okay, this is the simplest thing you can think of. You have n nodes, and between every pair of nodes, you flip a coin that lands heads and probability peak, and if that lands heads, you put that edge. So Erdős and Renyi back in 1961 showed something really cool about this graph. Essentially, you have phase transitions that occur in these networks. Okay? So specifically, if you add edges with a probability bigger than a certain value, you get nice things happening. If you add edges with a probability less than that value, those nice things don't happen. And this is a very sharp threshold. So they, in their 1961 paper, they showed, for example, that if you add edges with a probability that looks like this, log n plus r minus 1 log n plus alpha n over n, or alpha n some function. And if alpha n goes to infinity, no matter how slowly, so blah, 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 n, the resulting graph is going to have minimum degree and connectivity r, as applied to alpha surely. And if alpha n goes to minus infinity, again, no matter how slowly, the resulting graph is not going to have those properties. Okay, so essentially this alpha n going to plus infinity or minus infinity is what determines whether the graph has those properties. So this thing in the middle here is called the threshold. If you're adding edges with a probability bigger than that threshold, r minimum degree and r connectivity happen. If you add edges with a probability less than that threshold, those things don't happen. What's really cool is that that same threshold holds for R robustness. So essentially, if alpha n goes to infinity, no matter how slowly, at the same time you get R minimum degree, R connectivity, you also get R robustness. So essentially, all three of these sets coincide in a probabilistic sense in Erdős graphs. So when you get this much weaker property, you get this much stronger property. So it turns out, that was really cool because we didn't know anything about our robustness, right? We came to it because we were looking for when those algorithms will succeed. We identified that graph property. Then we started looking for that graph property and we found that it holds in Erdős networks. That's great. But it turns out that they also hold in a whole bunch of other networks that we're slowly starting to realize. Okay, so geometric random graphs, 1D least, preferential attachment graphs, random intersection graphs, 1D quantitative graphs. All of these things have this kind of crazy property that this much stronger robustness measure holds at the same time that our connectivity and our minimum degree do. Okay, so these graphs are basically, what these results are saying is that you gain a lot more. There's so much more structure to these networks than we had previously realized. So especially these types of large-scale networks will facilitate these local filtering dynamics when we apply them. All right, with that, I will stop.